Now, you must be wondering here that why sir said that cations will occupy the voids. Why not anions? Because you've read it in class 11. The size of the cation is always smaller than the size of the anions. And what I said you? In case of ionic compounds, as the anions are bigger, they will occupy the packing. Packing means at the corners. And the anions are bigger, so they will occupy the packing. And the cations are smaller, they will occupy the voids. Again I repeat, in case of ionic compounds, usually anions are present in the packing. Packing means, this word is there. See why I am using this word packing? Because you will be getting in the numericals. Packing, CCP, you will be getting it. So cubical closed packing. So when you will get this word cubical closed packing, CCP. So packing means atoms which is occupying the corners. We use the word packing there. Alright. So generally if it's an ionic compound, the bigger one, with the size which is bigger, the anions are bigger. So the anions will occupy the packing at the corners. Alright. That's the corners. We can say that. And the cations which are smaller, they will occupy the voids, we can say, because cations are small in size. Mind it always. Alright, it's very, very important. You will see it later on. I will say you another word I will use for packing at the corners. You should understand this word because I am repeatedly saying you will be getting in the numericals, and if you understand the word, then numericals will be very easy for you to solve. Okay, fine. Now let me come to what I was saying you, that radius of the octahedral void is 0.414 R, capital R. And radius of the tetrahedral void is 0.225 into capital R, where capital R stands for the radius of the atom. Now the question is from where we got it. Okay, I am going to derive it. So one I am going to derive it for you. Which one? The octahedral void, the bigger one. The smaller one I will give it to you, that is 0.225 capital R. You will derive it and you will show it to you. Alright, the bigger one I am doing it for you. Now tetrahedral void. Tetra means how it is? The 3 atoms will be there in this way and the 1 atom will be at the above. In 3-dimensional. But here how will I show? Here how will I show? Here I will show in this way, the 4 atoms. Total 4 atoms, na? 3 atoms will be in this way. The 3 atoms will be arranged, and the 4th one will be inside here. The 4th one, which you can't see. Alright, but here how will I show? In 2-dimensional. So in 2-dimensional, I am showing you in this way, the 4 atoms. Got it? Understand it? What I am saying? Here I am showing you in this manner. I have to draw it properly. There is no other option for me. Very poor in drawing. Okay, somehow I managed. So here the 4 atoms, tetrahedral. Mind it, I am talking about tetrahedral voids. You can see 4 atoms. In 2-dimensional, I have to show in this way only. The tetrahedral void, 1, 2, 3, 4. But in 3-dimensional, 3 atoms will be forming a triangle like in this way, and the 4th atom will be here. Alright? Clear? So, now this is your void, the one which I am doing it in blue. Alright? This is your voids, the one which I am drawing it in blue. So, here a little bit I have to do a merger. Yes. So, you can see the atoms, it's touching. Fine. Now, these are the center of the atoms. These are the center of the atoms, and this is the center of the void. Listen carefully, center of the void, which I am taking it as, let me write it here, I don't have the space, as O, and this one I will take it as A, and this one I will take it as B. And what will I do? I will join it, this one, I will join it. Clear? So here to here I am joining with the black. And the one for the atom I am joining with black, and for this one I am joining with blue, a dotted line, as you can see it. I hope you all might be seeing it. So why I am doing it, you will come to know. And this one again, it is black. So this one I have taken it as R, the radius of the atom. It is R. Got it? It is R. Now, and the radius of the void, I will take it as small r. The radius of the void, this is your small r. So this distance is small r. This distance is small r. Got it? So hence, what I can say is, here OA. OA is what? Capital R plus small r. See here, OA. This is small r and this is your capital R. So what is that? Small r plus capital R. Similarly, OB. OB is also capital R plus small r. Got it? Understood? O is the center of the void, A and B are the center of the atoms, and the radius is capital R. So radius is capital R, and the radius of the void is small r. I have taken it. This void is the blue atom. The blue, which one the atom I have drawn it, that is your void. Clear? Okay, fine. Now you can see very clearly it forms an isosceles right angle triangle. I do not have to say, because this R plus R, this is R plus R. So both the sides are equal. So it is isosceles. And here this angle will be definitely 90 degree. You know that it is isosceles right angle triangle. Okay, isosceles. You might have studied in maths. All right. So now in triangle OAB. Alright, in triangle OAB, if it is an isosceles, this is your right angle, understood? This right angle, isosceles right angle triangle, then this is your hypotenuse, AB is the hypotenuse, so it will be AB square is equal to OA square plus OB square. Now, OA is what? R plus small r, alright, whole square, and this one is also R plus small r whole square. So I can write 2 into capital R plus small r whole square. I can write it up. Clear? So now AB is what? AB is nothing but 2R. R plus R. It is nothing but 2R. 2R square. Clear? It is 2R square, you can say. So this one I can of course simplify it. I can write it as 4R square. I can write it as. Clear? So now what you can say, 2 and 2 cancel. So 2R square is equal to R plus R whole square. So square I can cancel it. So what I can write? That is nothing but, can I do it? So no, I can't do it in this way. It is 2R square. So I cannot cancel the square in this way. Rather I will write it this way. Root 2R whole square is equal to R plus R square. Then I can cancel the square and square. Because root 2, I have to take this 2 also within the square. Then only I can cancel it. I cannot cancel in this way. Alright. So I can write root 2 square is nothing but 2. Are you following? So instead of 2, I have written root 2 square. What is the problem? So root 2R square. So this and this cancels. So root 2R is equal to R plus small r. What I need to find? Small r. The small r is equal to nothing but root 2R minus r. So there R goes common. Here you can see R goes common, but it will be root 2 minus 1. Root 2 is how much? 1.414. Root 2 is 1.414. 1.414 minus 1. It will be how much? 0.414 R. So you got it? Small r is equal to 0.414 capital R. Is it? That radius of the octahedral void is equal to nothing but 0.414 into capital R, where capital R is the radius of the atom and the small r is the radius of the octahedral void. So I have done it for octahedral. I have said you to do it for tetrahedral, which is 0.225 R. The process is the same. It is the same process. The process is not at all different. It is the same process. Fine. Now from this what we come to know, as I said you, that the octahedral void is almost double. The radius of the octahedral void is almost double that of the tetrahedral void. That means what we can say, listen carefully this one. Many of the students they get confused here. Alright, so listen carefully. This is what I am going to say. Say what I said, that the radius of the octahedral void is 0.414 into capital R, and radius of tetrahedral void is 0.225 capital R. So almost double. I don't say exactly double, almost double it is. Got it? So hence what we can say, that is number of, listen very carefully, number of tetrahedral voids is equal to 2 into number of octahedral voids. Number of tetrahedral voids, listen carefully children, 2 into number of octahedral voids. Number of tetrahedral voids, because the space occupied by octahedral void is 0.414. Got it? 0.414. Listen carefully. And the space occupied by tetrahedral is 0.225. So 0.225 and 0.225. How many tetra you are keeping? 2 tetra. How many tetra? 2 tetra. You are keeping it in one octa. So if octahedral void is equal to x, number of octahedral voids, let us take it as x. Listen carefully. Then tetrahedral voids will be 2x. That's it what I said. That's it what I said. Suppose 0.414 and 0.225. We can keep almost 2 tetra. in one octa? 2 tetra you can give it or not in the place of 1 octa. So that's what I am saying. Let octahedral voids is equal to x. So tetrahedral voids will be how much? 2 I am keeping it. So it will be how much? 2x. Understood? Listen carefully this one and understand it. If any doubt, you can ask me. Got it? It's very important this concept is, because many of the children, they did not understand. They say, how it is 2 tetra, 1 octa, this, that. Got it? I'm saying you very, very important, because don't neglect this particular one. This is number 1 formula. That number of tetrahedral voids is equal to 2 into number of octahedral voids. When you do the problems when you do the numericals upon voids, it is very, very important. This particular one is. Got it? Clear? It's very important. So in this way. Next is, after that, number of octahedral voids is equal to number of particles in the closed packing. Number of octahedral voids. Number of octahedral voids is equal to number of particles in the closed packing. What I said to you, number of particles in the closed packing means number of particles at the corners. Number of particles in the closed packing means number of particles at the corners. Always the octahedral voids occupies the corners. Always octahedral voids, because it is, what you can say, bigger. Got it? Clear? Octahedral voids. Just now I said na 0.414. This is bigger. It occupies at the corners. Clear? And tetrahedral voids are smaller. This occupies at the center. We can say. So in this way, number of octahedral voids is equal to number of particles in the closed packing. Okay? Understood this particular one? This formula? It's very, very important. This particular formula is. Got it? This formula is. So now when we will be using it in the numericals, it will be much more. It will be used. So hence, children, it is very, very important. So next is, I will be coming to the next one. That is chart I will be giving you. That is, you will be having radius ratio. This you have to learn it, this particular one. Radius ratio 0.155 to 0.225, 0.225 to 0.414, 0.414 to 0.732 and 0.732 to 1. This is your radius ratio. Now, another column I will be drawing, that is your coordination number. You know what is coordination number? That is number of nearest neighbors. Correspondingly, the coordination number will be 3, this will be 4, this will be 6, this will be 8. Now, the name of, what you can say, the arrangement. The name of the arrangement. I have to write the name of the arrangement. Means it is geometry, so to say. What is the name of the arrangement? Name of this sort of arrangement. When 3 atoms will be there, then it is what known as trigonal. 3 means trigonal. Now 4 means tetrahedral. 6 means octahedral. 8 means BCC. You have read it. And BCC, the coordination number is 8. When the coordination number is 6, it is octahedral. 6 atoms are there, na? Just now I was saying. Tetra, it is 4, and if it is 3, it is trigonal. Now, then what are the different types of crystals coming under it? Okay, understood. The geometry is this, coordination number is, radius ratio is this. Trigonal, it can be anything. We don't have anything specific, we can say. One example I can give you, B2O3, that is boron oxide. Similarly, in case of tetrahedral, it is ZNS type. What I said? Generally, ZNS type, it is known as type. Got it? Now, octahedral means NaCl type. Alright, octahedral means it is NaCl type. And if it is BCC, it is cesium chloride, CeCl. Cesium. CSCl, cesium chloride. We can say that. That is cesium chloride type. This is cesium chloride type. Alright, so generally you will see in your numericals, you will say instead of BCC, the word will be cesium chloride type. That means it is talking about BCC. What is the coordination number? 8. What is the what you can say radius ratio? This. So if one word is given, the rest of the thing you can know. If BCC, then coordination number is 8. The radius ratio will be this. And what is the type? CSCl. So one you should know it here. Only one. If it is NaCl type, this is very commonly used. NaCl type in the numerical you will see it. Got it? So what is that? That means it is octahedral. And what is the coordination number? 6. And radius ratio will be this. Clear? Fine. In this way you will be getting it. Clear? So what are the other examples in ZNS type? This one I said, you know, B2O3, boron oxide. What are the other example in ZnS type? You will be getting CuCl, CuBr, CuI, copper salt generally, we can say that. Copper halides, HGS, barium sulfide, we can say that. In NaCl type, same thing. We can get NaBr, KBr, MgO, MnO, CaO, CaS. These are the compounds you will be getting it. Clear? And here you will be getting in CSCl type, you will be getting the copper. Again, that is nothing but that is CuI. There I say, sorry, copper I am saying, cesium. CSI, then that is CSBr, then TiBr and TiCl. Alright, CSBr, CSI, TiBr and TiCl. You will be getting it. Alright, so in this way you need to learn this particular table. You need to learn this table which I gave it to you for the radius ratio. Alright, thank you very much.